So question is, if u is equal to tan inverse of x plus y divided by root x plus root y, then show that x into dou u by dou x plus y into dou u by dou y must be equal to 1 by 4 sine 2u. So this is the question. So solution. So first consider u is equal to tan inverse of x plus y by root x plus root y. So from the question I consider this. So if it is a inverse trigonometry, it become now tan u is equal to x plus y. So simply bring tan inverse this side, it will become tan u. Okay, let's take this is equal to some z. Let's take this is equal to some z. Now z is a function in terms of y, x comma y. We can write it as x plus y by root x plus root y. So I considered the question, I sent tan inverse to this, it will become tan u, which is equal to x plus y by root x plus root y, and then this total term I considered as z. So if you observe, z is in terms of x and y function. So z is a x and y function. So just multiply with k in term kx and ky, which is equal to kx plus ky by under root kx plus under root ky. Okay, what I did, I simply multiplied every term with k. Just multiplied every term with k. Now if I take k common from numerator, I'll get x plus y. So here I can write it as root k into root x plus root k into root y. So okay, under root ab can be written as under root a into under root b. Under root a into under root b. So similarly, under root kx plus under root ky can be written as under root k into under root x, this part, plus under root k into under root y. Now already took common from the numerator. Now take root k common from the denominator. The leftover is root x into root y. So here k by root k into x plus y by root x plus root y. And if you observe this term, bases are equal, so powers are subtracted. The rule is when a to the power of m to the power of n, a to the power of m by a to the power of n, bases are equal and division is there, so we can subtract a to the power of m minus n. So this is the law of indices. So similarly, if you observe, this is also same, k, here under root k by k to the power of 1 by 2. Okay, so under root value can be written in the power k to the power of 1 by 2. So if you here power is 1, here power is 1 by 2, we can subtract, it will become k to the power of 1 minus 1 by 2, and finally it will become k to the power of 1 by 2. So I can write here, this total part I can write it as k to the power of 1 by 2 into x plus y by root x plus root y. So I finally got z in terms of kx comma ky is equal to k to the power of 1 by 2. Okay, if you see, this is what we assumed initially, where zx comma y equal to x plus y by under root x plus y. So I got k to the power of 1 by 2, and same this is a z. This is our z. Okay, so z is a homogeneous function. So if you observe, z is a homogeneous function, okay, of degree 1 by 2. Homogeneous function. Z is a homogeneous function with degree is equal to 2, 1 by 2. So here power k to the power of 1 by 2, so that becomes my degree. Euler's theorem actually. What is Euler's theorem? Euler's theorem says that if z is equal to x comma y, z in terms of function x comma y, okay, you take z is equal to any function x comma y, then according to Euler's theorem, we can write x into dou z with respect to dou x plus y into dou z with respect to dou y must be is equal to nz. N is a degree. N is a degree. According to what is this? This is a Euler's theorem. So according to what is Euler's theorem? Euler's theorem says that z is in function of x comma y, then x into dou z by dou x, see x and x, plus y into dou z by dou y, see y and y must be equal to n times of z. So in previous question, okay, in previous question we have z is equal to plus y by root x plus root y. This is nothing but tan u. Okay, this is nothing but tan u. Now according to Euler's theorem, I can write it as x into dou by dou x of tan u plus y into dou by dou y of tan u is equal to n. N is here 1 by 2. Z is again tan u. Okay, at the starting of the question we define tan u as x plus y by under root x plus under root y. So according to Euler's theorem, x into dou z by dou x plus y into dou z by dou y is equal to nz. Here z is tan u, so simply substitute in the place of z tan u, we will get this equation. Okay, so what is the dou by dou x of tan u? So dou by dou x of tan u is secant square u, but we are doing with respect to x again dou u by dou x. Okay, here be clear that tan in terms of u, but partially we are differentiating with respect to x, so treat it like tan x, but in the place of x we have u, so immediately do its partial differentiation. Similarly, y into dy dou by dou y of tan u is secant square u, but in place of y we have u. Okay, we have u, but we are differentiating with respect to y, so this can be written as dou u by dou y is equal to 1 by 2 times of tan u. Okay, so this is very important step. By applying Euler's theorem we got this. So simply partially differentiate. Okay, the partial differentiation of tan is secant square u. Okay, so dou u by dou x, because in place of x we have u, that's why dou u by dou x. Okay, similarly tan u is secant square u, but in the place of u, in the place of y we have u, so that's why dou u by dou y. Okay, here 1 by 2. 1 by 2 is previously we got k to the power of 1 by 2, so k to the power of 1 by 2 is the n value. Okay, so tan u is z, and after that from this entire equation if you observe, I can take secant square u as common, so this secant square u and this secant square u I am taking common, so leftover is x into dou u by dou x plus y into dou u by dou y, which is equal to 1 by 2 tan u. Clear? And then send this secant square u that side, then it will become x into dou u by dou x plus y into dou u by dou y is equal to 1 by 2 tan u. I'm secant square sending this will become by secant square u. So the next is simplification. X into dou u by dou x plus y into dou u by dou y is equal to 1 by 2 tan u. I can write it as sin u by cos u. Okay, secant square u can be written as 1 by cos square u. And then this part can be simplified as 1 by 2 into sin u by cos u. Similarly, if you reciprocate it, it will become cos square u by 1. So cos u and 1 cos u cancel. So answer is 1 by 2 sin u into cos u. So 1 by 2 and multiplying dividing with 2 by 2 into sin u cos u. So here I have sin u cos u. If I have 2 sin u cos u, I know 2 sin u cos u is equal to sin 2u. Okay, trigonometry formula. So 2 is missing, that's why multiplying dividing with 2. So if you observe this total part, this will become 1 by 2 2 is 4. This total will become sin 2u. So according to the question, what we have to prove? According to the question, we have to show that x into dou u by dou x plus y into dou u by dou y is equal to 1 by 4 sin u. So this is our proof. According to Euler's theorem, okay, we solve this. If u is equal to log of x square plus y square divided by x plus y, then show that x into dou u by dou x plus y into dou u by dou y is equal to 1. So this is your question. Okay. If you observe this is a Euler's theorem. What is Euler's theorem actually? If z is a function in terms of x comma y, then x into dou z by dou x plus y into dou z by dou y is equal to nz. Here n is a degree. So as soon as you see the question, you can identify it is a Euler's theorem. Euler's theorem. Clear? So for the purpose of Euler's theorem, I need to find first what is n. So here given u is equal to log of x square plus y square by x plus y. See, my right side part must be in terms of x and y. I have log. Okay, so if you send log this side, it will become e power u, which is equal to x square plus y square by x plus y. So if you apply e on both sides, it will become e power u, and e and log will cancel off. You will get only this part. Now I got e power u is equal to x square plus y square by x plus y. Consider it as some z. Okay, if you see according to Euler's theorem, z in terms of x plus y. Here also something in terms of x plus y, that is z. So my function z is equal to, in terms of x plus x sum and y, it will become x square plus y square by x plus y. So simply go with kx. So simply multiply with y every term. It will become kx whole square plus ky whole square by kx plus ky. So this step is very important. So in the place of x, I am keeping kx. In the place of y, I am keeping ky. Square square, and x is kx now and y is ky now. And if you observe, I can take Here I can take k square as common, then leftover term is x square plus y square. In denominator, if I take k as common, then leftover term is x plus y. K1 cancels and you'll get k in term x square plus y square by x plus y. Now if you see, this is my z. What is z? X square plus y square by x plus y. This is x square plus y square x plus y. Now z of kx comma ky, homogeneous function, I got k times of z. So what is the power of this 1? So I got degree n is equal to 1. I got degree n is equal to, because power of k is 1, so that will consider as n, the power is considered as n. Okay. Now according to Euler's theorem, what Euler's theorem says? Euler's theorem says that x into dou z by dou x plus y into dou z by dou y is equal to nz. If you observe here, z is e power u, y into here z is e power u is equal to n is 1 and z is e power u. Okay, then x into differentiation of e power u is e power u only, but in place of x we have u. See, this is not matching, so immediately partially differentiate, do u by dou x. Similarly, y into this part is e power y, partial differentiation, but we need to differentiate with respect to y again, so dou u by dou y is equal to e power u. Now I got x into e power u into dou u by dou x plus y into e power u into dou u by dou y is equal to e power u. So according to Euler's theorem, okay, I got this equation. So if you observe this equation, I can take e power u from this side. I can take e power u as common from this side. Then the leftover term is x into dou u by dou x plus y into dou u by dou y is equal to e power u. So I can cancel e power u, then on my final answer is x into dou u by dou x plus y into dou u by dou y is equal to 1. So this is my proof.